Welcome to the Dynamic Impact Test Procedures training class. This is a companion lecture series to go with the online course. I am Joseph Pelletier, the Chief Scientific and Technical Advisor for Crash Dynamics at the FAA. Just a real quick disclaimer. We're going to discuss some research opinions here. Anything that we say should not be construed to be a certification decision. For anything that's relating directly to certification, please consult with your local certification office. A quick overview, this lecture series, it's a companion to an online course which you should have already begun. For those in the FAA, you can access that course through ELMS and just search for the Aircraft Seat Dynamic Impact Test Procedures History and Background course. For industry, it's available through the designee registration system. And from there, you go to Design and Manufacturing Airworthiness, and you should be able to find this course by course ID 571. So the course also has the same name, the Aircraft Seat Dynamic Impact Test Procedures. Today's lecture series, we're going to discuss new and novel seating systems, primarily side-facing and obliquely oriented seats. This lecture will be provided by Amanda Taylor, a research engineer at the Civil Aerospace Medical Institute.
Good afternoon, and I appreciate you taking time to learn about how we come up with ways to protect occupants in unusual seating systems. So I've actually divided this into two parts, and part of that is just because of the virtual recording limitations, but also so that you get a little bit of the background and some of the research aspects. And then the other half will deal with more of the policy and the implementation. So first, I just want to go through a background on why we're even looking at this. And that's because when we have new and novel seats, sometimes they present injury risks that aren't as well protected using traditional means of compliance. So some of the forward-facing criteria, and we want to make sure that all occupants are protected even as we advance the seating system and structures around them. So seats continue to evolve and will continue to evolve as we get new types of aircraft, in particular, maybe the electric vertical and takeoff and landing vehicles. People are wanting to put in seats at different angles that are off axis compared to what's traditional. So based on the guidance, anything greater than 18 degrees with respect to aircraft centerline is actually considered a side-facing. It's not considered forward-facing. So we needed to address these new seats. We had some that were at 20 to 45 degrees, and then we have some that were strictly at 90 degrees. Some of these are single-place, some are multi-place. Some have a 3-point belt. Some want to use regular 2-point restraints. And these particular configurations are not addressed in the current regulations. So, like I said, forward-facing seats are defined as being oriented 18 degrees or less with respect to aircraft centerline. But all of these other seats that go from 19 degrees all the way to 90 are side and oblique seats. The way that people flail inside these seats or move with respect to the seat during the impact are presenting some different loading conditions than what we've seen previously. So when we were presented with these new and novel seats, the FAA put a research project together with the overall goal being to develop test procedures and injury criteria that can ensure occupants of these new and novel seat orientations continue to have the same level of protection as provided in occupants in the more traditional forward-facing seats. So we kind of broke it down into two research tasks. The first one was to determine what type of injury mechanisms. So what type of injuries do we expect to see, determine what the human impact tolerance levels of these injury mechanisms are, and then come up with a way to predict the occupant injuries in these seating systems during a survivable crash. The first part was to use a rigid seat mock-up based on information we got from industry. We asked industry what kind of seats you're installing, what angles you're installing at, and what kind of structure is around the occupants in these seats. The next part of this whole research project is to come up with ways where we want to continue to protect all occupants and all sizes, but understanding that you can't do the impacts on a crash test sled for all impact vectors. So coming up with advanced occupant models to simulate this response will then aid in certification later on. So the first one that we got was side-facing seats. And this was a test done at CAMI with one potential side-facing installation. And what we're seeing in this is new injury risks that we didn't expect, well, that we don't traditionally get in forward facing. So in particular, you can see we have now the head impacting the wall. We have occupant to occupant contact. Again, something not seen in traditional seating systems. And in that particular instance, we had some belt latch issues. You saw the test dummy on the far side actually came unbelted. And then in some instances, we see quite a bit of neck flexion. So if the neck and head is not supported during the impact, that's where you might get some very extreme flexion, as well as leg rotation. So if you rotate the leg too far, you're going to start having injuries. And then you can see where the torso of the test dummy is actually bearing on what is representing a either rigid shelf or an armrest or something. And so that's actually impinging into the abdomen of the test dummy. So that we would expect to see injuries with that. Now on the oblique testing, like I said, we went out to industry and we asked what kind of angles they were installing at. So we ended up coming up with two installation angles, 30 degrees and 45 degrees. And that's rotated clockwise with respect to aircraft centerline. We used a hybrid 2 initially to try to get a feel for just big picture kinematics, because the hybrid 2 is a little bit more robust, but he can't measure everything that the FAA-Hybrid 3 did or does. So we also used the FAA-Hybrid 3 to start looking at what kind of loading that we saw and what kind of injury risks we might anticipate based on what we're seeing. And in particular, the FAA-Hybrid 3 is more biofidelic in how he interacts. He's got the more biofidelic neck, and he has the ability to add a load cell at the T12 or mid-spine location. So in the CAMI testing, we had two different angles, and then we had two configurations in each. So the very first configuration, the structure stays the same. It's just whether or not we had a shoulder belt. But this is a scenario where an occupant is next to an interior feature that is rigid below the armrest level, down to the floor, and very flexible above it. So in particular, we had the interior feature emulated by a rigid half wall. The legs were restrained laterally at the ankles. And this is because what we had seen and been told by industry is that there would be structure that would capture the legs and not allow them to align with the aircraft with the deceleration vector. So we retained those with belt webbing. We used a conventional belt for the first configuration. And then for the third configuration, we added an upper torso restraint or a third point of restraint. The second and fourth configurations are an instance where the occupant seated next to an interior feature that holds the pelvis still and holds the legs still, but not the upper torso. So maybe a low shelf next to the test dummy or the occupant's pelvis. So in this instance, we still had the legs restrained because that's what we've been told. So we used webbing to restrain laterally at the thighs and the ankles. We used a body-centered belt and a conventional belt. And then, like I said, in configuration 2, we had no upper torso restraint. In configuration 4, we added the shoulder belt, so the upper torso restraint. This is one of the first instances. This is configuration 2. So that's no wall, no armrest, but also with no shoulder belt. And this was at 45 degrees with respect to aircraft centerline. You can see the occupant flailed quite a bit forward. And then we have quite a bit of rebound as well. So he managed to touch the floor and then rebound backwards. So some of the predicted injuries that we saw in these oblique situations were things similar to what we saw in the side facing. So when we had the rigid feature next to the test dummy, he's flailing over on top of it. We expect potential injuries to the sternum, to the pelvis. Anything that's going to contact that structure could have an issue. The legs, just due to the fact that the body is now moving separately than the legs, you might have some inertial loading, as well as more extreme neck flexion or even contact with structure around it. So now that we know what kind of injuries we think we might see, we needed to find what test dummies would be best to be used in these new seating configurations. So for the side facing, there were 3 different test dummies that were already being used by automotive. And that was the SID or side impact dummy, the Euro SID, and the Bio SID. And while all 3 test dummies produced similar injury criteria results, we saw that the US SID kind of lacked the ability, not only can he not measure the rib deflection or interact, we really didn't see that he interacted with the shoulder belts the way that we wanted him to. The Euro SID or ES was very durable and quite repeatable, as well as having the arms and the ability to interact with seats. And then the Bio SID lacked the durability and really can't evaluate any of the body-to-body contact. So we went out to the automotive regulations. So that's FMVSS, the Federal Motor Vehicle Safety Standards. 214 is the side impact protection section, and it specifies the ES2RE, which is newer than the one that we started the project with, but he evolved during the research project. And he was specified in Part 572, Subpart U. He has the ability to not only do rib deflection, but he can get abdominal forces as well as pubic symphysis force, and that's how much the pelvis is compressed. And that ability to evaluate the abdominal loading depending on the height of the armrest is really important, as well as having a very biofidelic head and neck to allow HIC assessment. The limitation that we had with him was that the neck injury criteria that he has are limited to fore and aft motion. And based on what kind of movement that we saw, we were going to need the ability to get it in side to side and interpret that high neck loads that we were measuring, specifically in the multi-place seats and any single place seat without full body support. So for oblique testing, we took a look at 2 of the most prolific forward-facing test dummies that are used for aviation testing. And that was the Hybrid 2 and the FAA-Hybrid 3. So one of the issues with the Hybrid 2, while he's durable, he lacks the ability to measure quite a bit in the way of neck loading in particular, as well as lower leg measurements. And those are both areas that we were concerned about. That's where the FAA-Hybrid 3 has a bit more expanded instrumentation capabilities, and it has the ability to put load cells not only in the neck, but also, like I said, in the T12 area, lumbar spine, and then we can get the femur and the tibia. So expanded capabilities. While we were looking at, there's actually a test device for human occupant research, and that's the Thor, which is, at the time we were using the Thor NT because that's the version that was loaned to us by NHTSA, and it was under development for use as the new test dummy for automotives. Development actually started back in the 80s, and it's just about completely approved for testing now. But one thing that the Thor has is the ability to measure, it's got over 100 channels of instrumentation. And he's the most advanced test dummy in the automotive community and is being used as a replacement for the Hybrid 3 for frontal impact testing. And they're actually on version M now, but it has a considerable instrument array, particularly in the thoracic and abdominal regions. And those are 2 areas that we're very concerned about in these oblique situations. When we got him in, we took a look at him statically. We wanted to see what kind of damage could occur to it, what kind of interactions he may have, because in automobiles, you don't typically flail in the same way that we do in the aviation environment. You know, he's really designed for more of a confined environment. So one thing you can see is he flails all the way forward, and now you're starting to impact some of his abdominal sensors on his upper thigh. You can see there's some of the upper instrumentation that gets rib deflection, would actually bind up just a little bit. Wires were being pinched just simply by manipulating statically. These are the potential issues that we saw. And then the lumbar spinal element is not really designed to flail forward in the same way that we were anticipating. And it has kind of these little shoulders in its design where there's little load concentrators, and we actually could see where the rubber might potentially fail at those load concentrators. We did not end up using him in the oblique testing, but we did test him vertically to compare how his vertical response compared to the Hybrid 2 and the FAA-Hybrid 3. So for oblique test dummies, we decided that the FAA-Hybrid 3, he's the only ATD capable of measuring most of the parameters that we were concerned about while still being pretty durable. And so based on the initial CAMI tests, we were concerned about that the standard forward-facing criteria won't quantify the injuries that we saw. So for part one, the whole reason that we started this is we saw these new seats and we saw new injury risks to the occupants in these seats. We wanted to do some initial testing at our facility in Oklahoma City and take a look at what type of injury concerns we might have based on conversations with industry and what type of structures and seats were going to be anticipated for installation. After evaluation and some of the testing, we found that the ES2 is the most appropriate device for testing, but he needed a little bit more injury criteria than what's used for standard automotive testing. And then for oblique, during our evaluation, we showed that the FAA-Hybrid 3 was the most appropriate and most durable for testing, but there were other injury risks that needed to be identified and then protected against.